Hello, this is Miss Moore, and today during chemistry we're going to discuss electrolysis. So today's essential question: how is electrolysis different from a voltaic cell? Electrolysis. In a voltaic or galvanic cell, we're talking about a spontaneous reaction producing an electrical current. Okay, a redox reaction, it's spontaneous. In electrolysis, the process is a process in which electrical energy is used to force a non-spontaneous redox reaction to occur. So when you think about it, electrolysis is exactly the opposite of a voltaic cell. Anions in the electrolyte solution are attracted towards the anode, where they undergo a process of oxidation. And electrons flow from the anode to the cathode, where cations undergo a process of reduction. Okay, let's do a really quick review on a galvanic or a voltaic cell so we can contrast that with electrolysis. Okay, so at the anode, this is where oxidation occurs. And so at this anode here, we're going to start with zinc metal, which is going to oxidize, producing zinc ions and 2 electrons. And these electrons, the zinc ions there, and the electrons go up that way. Okay, so the electrons keep going until they hit the cathode region. And in the cathode region, we're going to take our, in this case, I don't know why those all say zinc. That is a typo. These should all be copper. These are all copper 2+, okay? Just go with me on that one. So at the cathode region, this is where reduction is taking place, and the copper 2 ions capture a couple of electrons, producing copper solid. So the electrons into the solution, hitting the copper 2 ions, which then make solid copper. And this is a spontaneous process. Okay. Spontaneous process. That is a galvanic or voltaic cell. Okay, now let's compare voltaic cells with electrolysis. So in this case, we have the anode or the oxidizing end on the copper side and the cathode on the zinc side. And if we really quickly, so let me jot that down, this is the oxidizing side now. And this is the reducing side. And we can demonstrate that this is non-spontaneous because if we look up the standard reduction potentials for, well, if this is oxidizing, we're going to have copper solid produces copper 2+ and 2 electrons. And the reducing side, we would have zinc 2+ plus 2 electrons, giving, produces zinc solid. Okay, the standard reduction potential for zinc is, or zinc 2+, is going to be negative 0.76. And for the copper side, we have positive 34. And if you remember, E cell equals E cathode minus E anode. And if we do those calculations, we come up with an E cell of negative 1.1 volts, which is extremely not spontaneous. So we need to use some sort of energy electricity, battery, something to make this happen. Let me clean this up for a bit and then we'll continue. Okay, so what we have here is this battery, or it could be electric current as well. And you'll note that the positive terminal of the battery is connected to the anode. What that's going to do is force, or you can think of it as pulling electrons, okay, forcing the electrons, which will then create some copper 2 pluses. When the electrons get to the negative end, it's going to force the electrons away from the negative, so the electrons will keep going down this way. Nope, not in there. Let's try that again. Here. And then from here, these electrons are going to hook up with these zinc ions, producing zinc solid. So the process, the idea is the same. And the electrons still move from the anode to the cathode. The difference is with a galvanic cell, this is a spontaneous reaction. And with electrolysis, you actually need some sort of energy, you need some sort of current to force the whole process. Okay, so that's the major difference between electrolysis and galvanic cells. All right, so a little summary about the difference between the voltaic or galvanic cells versus electrolytic cells. So all electrochemical cells, both voltaic and electrolytic, oxidation occurs at the anode, reduction occurs at the cathode. Now for the differences. For a voltaic cell, the anode is the source of the electrons. Okay, the anode itself is the source of the electrons, and it has a negative charge. The cathode itself draws electrons, and it ends up with a positive charge. For electrolytic cells, electrons are drawn away from the anode. Okay, they need to be drawn away, which must be connected to the positive terminal of an external power source, which then makes the anode positive. And electrons are forced to the cathode, which must be connected to the negative terminal of a power source. Thus, the cathode is negative. Okay, let's try a quick little tiny example on electrolysis. So the question is, predict the half reaction occurring at the anode and the half reaction occurring at the cathode for the electrolysis of a mixture of molten MgBr2. All right, so we'll start with oxidation. Which would be the anode. Now, between the Mg and the Br, which would be most likely to oxidize? Remember, oxidizing is losing electrons. So who's going to be more likely to lose? That would be the bromine, right? Bromine is bromine ion, right? So Br is much more likely to lose an electron. So we're going to have Br loses an electron to become Br2 plus 2 electrons, so we got to put a 2 here. Okay, and then the reduction, or the cathode, is going to be the magnesium. So magnesium ion plus 2 electrons is going to give us magnesium solid. Okay, so it's just a real quick little practice. The really important part of this lecture is to understand the conceptual difference between electrolysis and galvanic cells. All right, and the last topic for today is the stoichiometry of electrolysis. So Faraday found that the mass of product formed during electrolysis is proportional to not only the amount of electricity used, but also the molar mass of the product. So guess what that means? The amount of product produced or the current needed can be predicted using basic stoichiometry. And of course, these are slightly more complicated than our basic stoichiometry, but not too bad. All right, so a few useful relationships. So first of all, 1A equals 1C over S. What the heck does that mean? It means 1 ampere equals, so A is an ampere, and it's the amount of current flowing. So usually when you give an amount of current, you'll say, 2 amps, something like that. But that's related to C, which is the quantity of electric charge. You can actually kind of get electric charge out of that, which, electrons, that's sort of important. So 1 amp equals 1 charge per second. Okay, and then we have another relationship, which is Faraday's constant. So 96485 coulombs per mole of electrons. Totally, hugely important. It'll help us out a lot. Faraday's constant, this is found on your, not you, let's try that again, on your reference table. And F relates to charge and moles of electrons. All right, let's try a practice problem. Gold can be plated out of a solution containing Au3+ according to the half reaction given below. Big question, what mass of gold is plated by a 25-minute flow of a 5.5 amp current? All right, so we have 2 different units we want to cross out, right? We have 25 minutes and we have 5.5 amps, and we're trying to get to mass of gold. The best way to start this is to start with time. And let's try to get rid of that minute unit. So we have here 25 minutes. Make this nice and huge over 1. So what do we know about minutes? Also keeping in mind, if we go back to our 2 helpful relationships, we have second right here. And we have amps here. So if we can get to seconds, we'll be able to cross it out when we start trying to cross out our 5.5 amps. All right, so 25 minutes. Well, I know that 1 minute is 60 seconds. So I've now crossed out my minutes. And I'm at seconds, which can be useful in a few. All right, so the next thing we want to deal with is 5.5 amps of current. Well, let's go back and look at our useful relationships again. We see here that 1 amp equals 1 coulomb per second. So if I have 5.5 amps, that's the same as having 5.5 C per second. So we can use that. So I'm going to put 5.5 C per second, and yay, our seconds cross out. So now I'm at C. So do we have a relationship with C? Now we're trying to get to mass, right? So C, what did C equal? Let's go back and look at those relationships again. All right, we have here 96485 C over mole E. Handy. We need a C, and we actually need moles too, so we're moving in the right direction here. So I want the C on the bottom, so I have 96485 C on the bottom and 1 mole E on the top. So C's cancel out, And we're left at mole, and hopefully this is starting now to feel like familiar territory. We want to get to mass gold, but we're at moles, electrons, and look right here. We have a coefficient with our E, so we can say 3 mole E equals 1 mole AU. And oh my goodness, moles cross out, mole E crosses out mole E. So now we can use the molar mass of gold, 1 mole AU, and molar mass of gold is 196.9, that's not a 9, 97 grams AU, mole and mole cross out. Oh my goodness, I think we've got this. All we got to do now is plug it in the calculator and see what happens. And I got, with 2 sig figs, 5.6 grams of gold. So there is a practice problem with stoichiometry of electrolysis. These are not overly difficult, but you really got to think about it, particularly because you're mostly going to have 2 different units that you need to cross out, or conversely, you might start with 1 unit and have to get down to 2 units. So you got to keep track of several things at once. Okay, this really isn't too bad. Slow and patient. All right, that's it for today. Have a good one.